Okay, this week we're talking about vertical curves. And just like the last couple weeks, I want to call your attention again to the Hickerson book, Route, Location, and Design. Just like horizontal curves and spiral curves, Hickerson does a really nice job covering a lot of the details and minutiae of vertical curves. So a vertical curve is used to smooth the transition, right? Just like a horizontal curve allowed you to change a direction from one bearing to another bearing at a high speed, um, a, a vertical curve allows you to change gradients. So you can be going down a steep hill and preparing to go up a steep hill, and we'll throw in a smooth transition between there, and that's called a vertical curve. And they can either be a sag environment like this, where you're transitioning from a down gradient to an up gradient, or it can be a crest vertical curve like you see immediately after that to get up over a hill. And the the geometry of a vertical curve is based on, right, the design speed that we're trying to facilitate travel on that road. So just going over the elements of the vertical curves, we're going to be dealing exclusively with symmetrical vertical curves. I will just call out here in a couple slides a non-symmetrical curve, but this is the basic geometry for your symmetrical curve, and some of these elements are going to look real similar to the horizontal curves. We have two gradient lines now. We called these tangent lines in the horizontal curve scenario, but now these are called gradient lines. These are the straight hills, either coming downhill or going uphill. And where they would project or mathematically intersect, we call that the PVI, the point of vertical intersection. Right? Where the curve begins, we call it the beginning of the vertical curve, and where the curve ends, we call the end of the vertical curve. Um, this is one of the distinctions between horizontal and vertical curves. L is the length of your vertical curve, but it's not the actual arced or curved length like it was in a horizontal curve, right? In this case, in a vertical curve scenario, L is the horizontal distance from the beginning of your curve over to the end of your curve. And what makes a symmetrical curve symmetrical is not that your elevations and your gradients have to be mirror images of each other. It simply means that the distance from the PVI is equal back to the beginning of the vertical curve and to the end of the vertical curve. So that distance from the PVI to one of those two ends is simply L over 2, or 1/2 of your L distance. E is the vertical distance from the PVI, or where your gradients intersect, up to or down to, if it's a crest curve. It's the vertical distance from the PVI to the curve design location, or design elevation. X distance is it's a horizontal distance from either the beginning of your vertical curve out to a random station of interest, or it's a distance from the end of your vertical curve out to a random station of interest. And at those specific x distances, we then have what are called y ordinates, or y offsets. And y dimensions are the vertical distance from the gradient line up or down to the design curve elevation. And vertical curves, they also differ from horizontal curves in that they're not arcs like horizontal curves were. Vertical curves are actually parabolas. And if you think about a cone, right, if you slice a cone with a direction perpendicular to its central line, you would have the resultant circle. But if you take that slice and cut it down at an angle, from one side of the cone down to its base, that resultant is not a circle, it has a changing radius, right? Because you're slicing it into the cone up here, which has a smaller radius, than down here, which is a bigger radius. So the resultant figure is actually a parabola. And Hickerson and some other books, you'll see vertical curves actually referred to as parabolic curves. So these are some examples of the different geometry you can see. These scans come out of Hickerson, and obviously these gradients are not mirror images from one another, right? Your incoming gradient is at a flatter slope than your outgoing gradient, but this is still a symmetrical curve, right? Because it simply means from our PVI here, the distance out to the beginning is equal to the distance out to the end. And you don't have to have opposing gradient, positive going into a negative or vice versa, to have a vertical curves. You can have all sorts of configurations. This is your traditional sag curve, right? Negative coming in, positive going out. You could also have a sag curve with two negative gradients, right? Negative coming in and a different negative going out. You're still needing to smooth that transition between gradients for vehicles. Crest curves are when you have a positive coming in, negative going out, and this is the traditional crest curve geometry, but similarly you could have two positives or two negative gradients requiring a crest curve that connects those two. And all of these different variations down here could still be considered symmetrical curves, right? Symmetry has nothing to do with these gradient lines. It only refers to the distance from this beginning point to the intersection point to the end point. And these are all symmetrical curves as well. You can even have some examples where a gradient has zero slope, right? Maybe you've got a flat design gradient coming out here, and the highway is going to continue on, across Iowa or North Dakota, and you're still connecting, right, a parabolic curve between two gradients, even though one of those gradients could, in theory, have a 0% slope. So this is the only real mention we're going to make of non-symmetrical curves. This diagram comes out of the textbook, so they do spend a little bit of time talking about it. But when your PVI is not equidistant back to your PVC and your end of vertical curve, right, you have a different L1 and L2 distances, you treat it as if it were two independent symmetrical curves, right? So from the PVI to the beginning of vertical curves, that is treated as one symmetrical curve with its own L distance, and the PVI to the end of vertical curve is a different symmetrical curve with its own L distance. And that's really the only change here. Most of the math that goes into computing elevation of your stations along a vertical curve are the same. So we need to talk about gradient lines, because that's where the calculations begin. And the gradient is simply the slope of a line, right? It's another way of expressing slope. Right? And we talked about slope back in slope staking. There's different ways to express slope. Percentage, ratio, decimal, but it's all calculated the same. Slope is equal to rise over run. You've known that since high school or middle school geometry. And now the rise is simply the change in your elevation, and the run is your horizontal distance. So I'm just going to work through an example here throughout the rest of these slides, and this example comes straight out of the textbook, so you could follow it along through the textbook as well as you do your reading this week. We're given this example here of two gradient lines. And gradient lines are generally identified by the PVI stationing and elevation. Next PVI station and elevation, and then the last one. And when you have three points of vertical intersection, you have two gradient lines, and you can compute a gradient difference between those two. So the gradient of your first line, or the slope of your first gradient line, I should say, G1, is simply computed by taking the difference in elevations, right, and dividing it by the difference in stationing, because that gives you your horizontal distance. And if you do that for this example, you're going to get a positive 6.38% slope. G2, the gradient line going out, is again difference in elevation over difference in stationing. This time we're descending in elevation, so we have a negative elevation change. And these signs are going to become really important with vertical curve calculations. So always pay attention to your algebraic signs here. But we have a flatter gradient, a flatter slope. It's a negative 3.54%. The difference between gradients is a variable that can be used in some vertical curve calculations, and some books call this variable A. Our textbook does not. Hickerson does call it A. I know I've referred to the Iowa Department of Transportation Survey Manual for a really good source of information on curves and spirals, and they also have a chapter on vertical curves. They refer to this difference between gradients as A. But the difference between gradients is simply, this is my mistake, it should say G1 minus G2, and that's consistent every time you take this difference. You take the incoming gradient minus the outgoing gradient, so that should say G2. And that's equal to 6.38% minus your negative 3.54%, right? Pay attention to your signs. Negatives become important because the difference between these gradients is positive 9.92%. So I wanted to, before we go on with calculations, I wanted to just kind of take a step back and describe the process of computing vertical curve elevations here. So what we've done is we've looked at an example where we've been given this information so far, these three red dots, or actually we've been given PVI elevations, right? So your BVC does not necessarily, well, it will not start at a PVI. So our next PVI is somewhere up here, and our gradient line comes in, and then the gradient line goes out. And the next PVI is out here beyond, right, your end of vertical curve. But what we want to do, the first step in these calculations, is to calculate elevations along these gradient lines. Where we go along these gradient lines, how far we go, is completely dependent upon how often, a contractor needs information to build this curve correctly. It might be every half station or every 50 feet. If it's a small, tight urban curve or in an urban road, maybe it's every 10 feet if it's a steep curve. So that's completely independent on the construction needs. But once you've calculated the elevations along these straight gradient lines, our next step is to compute these y ordinates, these y offset dimensions from the gradient line up to the design curve. And we'll be doing that here in a second as well. And if you have the elevation of your gradient line and you have the vertical offset between the gradient and the actual curve, well, then you're simply adding or subtracting two numbers to get elevations up here along your design. geometry. And once you have a series of design elevations spanning your vertical curve, you basically define your vertical curve for somebody. So that's the process we're going to work through here. A quick word on units. Our book is a little different in compared to, I think, how most everyone else works through vertical curve calculations. And it has to do with how you're expressing your slope units or your gradient units and your distance units. And if your gradient is expressed in percentage form, then you have to express your distances in stations. And for example, if G1 equals 6.38%, your distance would be expressed something like 4.05 stations. But if you're doing something a little more conventionally, the way we usually work with calculations, if your gradient is in a decimal form, your distance would be expressed in feet units. So with these exact same numbers, in decimal form, G1 would be 0.0638. And if that's how you're expressing your slope, then you would express your distance as 405 feet, not 4.05 stations. I think this is generally how most people are more comfortable expressing things, keeping slope in terms of a decimal form and just feet being feet. But that's not how our textbook does it. Our textbook runs all these calculation examples by keeping slope in percentage form, and all distances are expressed in stationing. So I'm going to be consistent with the textbook here for you as you're following along in the reading. But this is not how I would do it personally, and it's not how Hickerson does it, nor how I think most other resources would do this. Okay, so the first step was, like we talked about there a couple slides ago, is to calculate the gradient line elevations. Right? And we're going to keep working with the same example that we started on at the beginning of this. We were given those 3 PVI stations, right? 21 plus 50, 26 plus a pair, and 29, 25. And we calculated, based on the stationing and the given elevations, that this G1, this gradient line, was 6.38% positive, and G2 is negative 3.54%. So once you've got your slopes calculated for your gradient lines, then you're going to need to calculate the elevation along that line at whatever station interval is required. And the example here that's going to be worked through is every 50 feet, or every half station. Right? So I honestly don't care how you go about this. Everyone has kind of their own personal preference. I would hope by now that you're able to recognize how easy it is to calculate the difference in vertical elevation change between 2 points along a straight line. Right? We know slope is rise over run, which is equal to change in elevation over horizontal distance. And right now, what we're interested in calculating is this change in elevation. So if we re-express this equation algebraically, your change in elevation is simply your slope times the horizontal distance. Right? If you want to know what's the difference in vertical elevation change from this point to that point, you simply multiply the slope of that line times the horizontal distance between those 2 points. This is really easy when you're leaving your numbers in percentage form, because remember, what does that percent symbol mean about this number? Right? When you express a slope in percentage, that means for every 100 horizontal feet, you're rising 6.38 vertical feet. Well, that's real easy. Right? If you know the elevation that you're starting at, and you need to calculate the elevation of a point 50 feet away, well, that's half of this number, 3.16, or 3.19 feet difference between this point and 50 feet away. Or if you're going every 100 feet, then it's 6.38 feet. Really, really easy. So what a lot of people prefer doing is starting at a known elevation and then just simply adding that common interval, right? 3.19 feet every time, all the way up until they get to their PVI. And then once you get to your PVI, your slope changes. Now we're at a negative 3.54, which again just simply means, because it's percentage, for every 100 horizontal feet we go, we drop 3.54 vertical feet. So if you're going every 50 feet, you have that number. And that would be, what, 1.72 feet. So every 50 horizontal feet, I'm going to descend in elevation 1.72 every time until the end. So that's how I would do it. I think that's how most people prefer to do it, because it's a common sense approach to gradient line calculations. This is the example out of the textbook. They're basically starting at the gradient elevation, right? And then using that in the equation every single time up until the PVI. And they're applying the slope, 6.38, times the distance in stationing, always from the beginning. That's why they're going half a station, and then one full station, and then 1.5 stations, and 2 stations, and so on, all the way up until 4 stations away. And then they get to their PVI. So if you're going to do that, don't accumulate your elevations. Always add your vertical change to the beginning of that gradient line, if that's where you're going to express your distances from. Doesn't matter to me. I've spent probably too much time already on a pretty simple calculation, but do whatever is comfortable and makes sense to you. Okay, we're going to get into a couple calculations that relate to the variables on these parabolic or vertical curves. And we talked about E. E is that vertical distance from the PVI up or down to the design curve elevation. And parabola geometry would tell us that E is equal to the difference in your gradients, G1 minus G2, times L, which is the length of your vertical curve, divided by 8. Or, if you're looking at a resource like Hickerson, G1 minus G2 is expressed as the letter A, or A times L over 8. And then R is a new variable. R relates to kind of not the radius like it did for horizontal curves, because this is a parabola, so we don't have a radius. What we have is a rate of radial change. So this is kind of similar to a spiral. If you remember what a spiral was in a horizontal curve, a spiral connected a straight line tangent to a circular arc, and it increased its radius from infinity when at the straight line out to the radius of the circle at the curve. Right, so it had an ever-increasing changing radius. And that's similar to what's going on here with this vertical curves R, which is the rate of change. It's less steep out here at the gradient line, where it wants to ease a driver into the transition from climbing up a hill and into this curved transition. And then as you proceed along this parabola, it's getting kind of a sharper or steeper radius or rate of change. And once you hit the middle of your vertical curve, your halfway point, you've hit the sharpest rate of change, the most severe rate of change. And then you're going to ease your way back out and get ready to get that car back onto another straight line. If you just went straight in a vehicle going 80 miles an hour down the interstate on a hill going up and straight into an arc of one consistent radius, you'd create launch angles out here, and it would not be a safe transition. So you have to ease those cars into that curve and ease them back out. Think of R like the difference between velocity and acceleration, right? Velocity is equivalent to the radius of a circle. It doesn't change. Velocity is one constant speed, say 50 miles per hour or 10 feet per second, maybe something that you could walk, 5 feet per second, I guess. Rate of change is equivalent to acceleration, where you know the feeling of a car going at a constant speed versus a feeling of a car accelerating, right? You feel that kind of man-made gravity effect on your body. And acceleration is a rate of velocity changing. And as you're getting up to the maximum speed you want to travel, you're constantly accelerating from 0 up to your highway driving speed. And that's what's going on with rate of change here. You're going from a flat rate of change, increasing it to a steep rate of change, and then decreasing back out of rate of change. Y is the vertical ordinate offset, or this vertical distance from any random station, right, from the beginning or the end of your vertical curve, measured horizontally out to a station of interest. And it's that vertical distance from the gradient line down to the design curve elevation. And that vertical distance y is simply equal to the rate of change r times x squared, where x is that distance from the beginning or the end. And again, expressed in stationing, not feet, because up here when we computed r, we're going to use g1 and g2 expressed as percentages of slope. And now's a good time just to kind of call attention to the differences between horizontal and vertical curves, specifically L and R. Each curve has an L variable and an R variable. And in a horizontal curve, L was the arc length, right? The total length of your horizontal curve from PC to PT as measured along that arc. And that's a big difference between, or compared to how we call L in a vertical curve scenario. Now L is the total length of curve still, but it's measured in a horizontal perspective. So it's no longer measured along the arc. It's measured horizontally as the crow flies on plans. The other big difference is R. In a horizontal curve, it's capital R, and it refers to the radius, right? And it's a constant dimension. This arc has a constant radius the whole way along there. It's little r in a vertical curve, and it's not a radius, right? We just spent time talking on this. It's the rate of radial change as you proceed through the parabola. So that's always a really good test question, is to have people explain to me the differences between a horizontal and vertical curves, L and R variables. Okay, so calculating the vertical curve. This is straight from the example in the textbook, and these are the calculations or the equations that we just kind of covered. And this is the calculation that we did at the beginning of this slideshow, where we computed your G1 gradient and your G2 gradients. We're going to work through the example given this information, where the PVI occurs at station 26 plus a pair at elevation 655.06, right? That was already given to us. We used that information to calculate G1 and G2 already, and now we're saying this is what the design speeds or the design criteria requires, an L distance of 4 stations, or a 400-foot long vertical curve connecting these two gradient lines. And these are the steps that you go through to calculate elevations along a vertical curve. This comes straight out of the textbook. So we're going to start with number 1. And number 1 is to set up a table to record these calculations. This lends itself really nicely to a spreadsheet if you prefer working your calculations that way, but you're just going to have these columns: your point, your station, the gradient elevation that you've already calculated, and then the computation for y, your y offset, which is ultimately used to determine your curve elevation. Step 2 is take the information that you already know and start to populate your table, right? We know our gradient lines had a PVI1 at this station and that elevation, a PVI2 at 26 plus a pair and that elevation, and a PVI3 at this station and that elevation. And you're going to set up, or for this example, we're going to go every 50 feet, right? We started at 21 plus 50. We're just going to go every half station all the way from the PVI1 out to PVI3. And we were told that this curve, its PVI is 26 plus a pair, and it has an L of 4 stations. And think about what that means, right? If this is a symmetrical curve, that tells us the beginning of the vertical curve occurs 2 stations before the PVI. And the end of the vertical curve is 2 stations after the PVI. So, if this is our PVI, 26 plus a pair, we know 2 stations, 24 plus a pair, is where we're going to begin our curve. And 2 stations after 28 plus a pair is where we're going to end our vertical curve. So this is your 400-foot vertical curve. It's your 4-station L distance. Step 3 is calculate your R value, because R is that rate of change between these two gradients. And it's G1 minus G2 over 2L. Remember that note about the units. Keep your gradients in percentage form, 6.38 minus your negative 354, and keep your distance in stations. So 2 times L is 2 times 4 stations, or a rate of vertical change, or rate of change of 1.24. Step 4 is to compute your y dimensions at each station from beginning to end of your vertical curve. So just like the equation we looked at a couple of slides ago, y is equal to your r value times x squared. And this is the one step that can be a little confusing. We said back then x is that distance, the horizontal distance, expressed either from the beginning of the vertical curve or the end of the vertical curve. And what you want to do is express it from the beginning of the vertical curve out until you reach your halfway point, and then you want to express it from the end of the vertical curve, from the halfway point out to your end, right? So you can see here in your equation, y equals r times x squared. R is the same for all stationing along here. It's 1.24 the whole way down. And your x distance is going to increase from the beginning of vertical curve. Well, it's 0 because you're at your curve. You're not going any distance away yet at 24 plus a pair. 50 feet later, at 24 plus 50, you've gone half a station. 25 plus a pair, you've gone 1 full station. And 25-50, you've gone 1.5 stations. Out here at your PVI, you could actually compute E using the equation for E, or you could simply do y equals r times x squared, where x would be 2 full stations. And then you're working kind of backwards, where now your x distance is as measured from the end, so we're 1.5 stations away from the end, 26 plus 50 down to 28 plus a pair, right? And then when we proceed up to 27 plus a pair, we're only 1 station away from the end, and at 27 plus 50, we're half a station away from the end. So here's another good example of where you can see the symmetry coming into play here. This is a symmetrical vertical curve. We go 0, 0.51, 1.5, and then we repeat that 1.51, 0.50. The calculation's real simple. R times x squared will yield these values. And again, because this is a symmetrical vertical curve, your y values should exhibit symmetry from 0 to a maximum and back to 0. Last step is to apply this y dimension to your gradient elevation to obtain the curve elevation. So you're simply taking your gradient elevation and you're always subtracting y. And I say always subtracting y because in a crest curve example like we have here, right, we have a crest curve connecting these two gradient lines. Our gradient elevation is above the design elevation. And if our y value is positive, we're subtracting that value, so we're actually going to get a lower elevation along our curve than we had out here at the gradient line. And the opposite is true in a sag scenario, where if we had a V-shaped valley with a gradient coming down and going up, you would have a negative G1 and a positive G2, which would give you a negative value ultimately for your R. And if you have a negative rate of change, you're going to have negative Y values. But that's okay, because when you subtract a negative Y value, you're actually going to be going up higher elevation from your gradient line to your sag curve. And that makes sense if you draw it out and look at it in a picture. So don't worry if you have negative y values, that could be right, and always subtract your y values when you're computing curve elevations. This is what it looks like visually, right? We just kind of explained that, where this y dimension goes from our gradient line down to the curve dimension, location. We don't have symmetry in the final elevations here because your gradient lines are not equal. This is not drawn very good, right? Remember, we calculated this incoming gradient to be 6.5%, and this outgoing gradient should only be half as steep, because it's like, what, 3.5% coming out. So even though your y dimensions will be symmetrically equivalent to one another, your ultimate resulting elevations along the curve will not be if your gradient lines are not equal to one another, right? You'll be imbalanced, which is why we're at a 645 at 24 plus 50, but a 649 at 27 plus 50. So the last thing to talk about here are high and low points on a vertical curve. Let's just go back here. Again, this picture is not great because it looks more symmetrical than it really should be visually. But the high point of a crest curve is just that. It's what's the highest elevation attained along a vertical curve. And in a sag curve, right, it's what would be the lowest elevation that would occur. And it's not always at the PVI. Actually, it's never at the PVI unless that gradient slope is equal to that gradient slope. But that's never the case, right? You have different magnitudes of slope. So So your higher low point will be skewed left or right, and we'll look at examples of that here in a second. But high and low points are important really for clearance and drainage. So those are the two big reasons, right? On a crest curve, right, overpasses are the most common thing. You kind of want to know what's that separation distance from your decking down to something that might need to travel underneath the roadway. Similarly, in a sag curve, if you've got a low point in your road, that's where water's going to go. And that's where you're going to need to put in a storm drain inlet. And it's kind of interesting to start looking for these things now as you go around town or drive down highways. Look and see where they're putting culverts, where they're designing a high point of an overpass to be, right? Is it directly over top of the railroad tracks? Probably is. And how did they achieve that arc with the gradients coming in and out, right? Did they have to build up ground to produce or to make artificial gradients with the roadways? It's really interesting to see how we've terraformed the natural world into living, livable features. And this obviously is Pittsburgh here on the right. And when I go to Pittsburgh and visit, I look at it as an exercise in geometry, right? Look at the horizontal and the vertical curves and the spirals and everything that's been done to terraform this little point between two rivers into a place that can accommodate 2 million people moving at the speed of life, right? And this picture on the left here is Houston, I believe, and it's neat to see all of this geometry come into play. Here we obviously have horizontal curves. I'm sure there are spirals built into these curves to facilitate the high speeds. In addition to the horizontal curve, you've got this ramp also undergoing a vertical curve to get up and over all of these other lanes of traffic, and it's really a marvel of human design that can take, that can simplify a very complex means of travel and break it into spatial segregations horizontally and vertically with simple geometry, right? And I'm not saying this was easy to do by any means. I couldn't even begin to understand how this was designed. But what I can understand is that every single element in this overall design is simple in nature. It's simple geometry, and it's no different than the exact examples that we've been working through for horizontal and vertical curves. So, back to our high and low points. This is what I mean when I say it's going to be inconsistent with the PVI, right? Your higher low point will be skewed towards the flatter gradient. And that's what this little bullet point in the textbook says, is that when you've got a flat gradient, it'll pull that low point towards it. So you won't necessarily have a higher low point occurring at a nice even stationing, and it'll never occur here at the PVI. So where that occurs, the station of your higher low point is determined by this equation here, and x represents the distance from the beginning. It's always from the beginning here now, from the beginning of your vertical curve out to wherever that high or low point is. And x is equal to your incoming gradient times the length of your vertical curve divided by the difference between your gradients, or the A dimension if you're looking at a book that calls that A. So the steps to compute a high or low point are: 1, draw a sketch and label what you know. Right, you're probably given your PVI elevations and or your gradient elevations. So draw it out, sketch it, and then once you've sketched it, you can visually note where that higher low point is going to occur with respect to your PVI. Is it going to be pulled towards the beginning, or is it going to be pushed beyond or after the PVI, towards the end of the curve? Okay. Next is you solve for that x distance, where x is what we just looked at. Then you're going to repeat the steps that we already did, we already looked at. It's the identical calculations. Once you know the station that your higher low point occurs, then you need to compute the elevation of your gradient line at that station, and that's just the elevation along that straight gradient line between your PVIs. Once you have your gradient elevation, right, then you can compute the y offset from the gradient line up to or down to the curve. And once you have your y offset, you simply apply that y offset by subtracting it from your gradient elevation, and that will give you the elevation of the curve at the specific high or low point. So the only difference here in the calculations that we've already looked at is how you determine x. Right? In the example we worked through, x was every 50 feet. Now x is a very specific distance based on the geometry of your curve data. We're going to have a little bit of homework this week so I can get you practice on calculating gradient elevations, and then the lab this week will be looking at an indoor lab where we're going to be working through calculations on vertical curve stationing.